In this lecture, I want to talk about the first derivative test and how we can use the derivative of a function to determine if we have a maximum or a minimum. What we're looking for is called relative extrema. All right, and an extrema just could be a max or a min. So, for example, I might have a function, just to draw a quick graph, something like this. All right, we would consider this graphically to be the relative maximum. And what I mean by relative is just if you look in an area near that point, it's the largest function value in that area. It's not the largest function value overall, because I've got some points over here that are bigger, right? Those are larger function values than what I have here. But if I go a little bit to the left or to the right, the function values decrease. So that would be a relative maximum. Likewise here, I would have a relative minimum. If I go a little bit to the left, the function values get larger, or if I go to the right, the function values get bigger. It's not the absolute minimum, because I have points over here that are smaller. So that's what we mean by relative. We just mean kind of in an area right around that point, it's the largest or the smallest value. So how do we use the derivative to help us find these? Well, when we talked about increasing and decreasing functions, we found that if for a point C, all right, if f prime of C, we'll call C, well, it's any point in some interval AB. If f prime of C was positive, then f was increasing on the open interval A to B. So C is just any point in AB. And then if f prime of C was negative, then f is decreasing on that interval. All right? So if I pick any point in here, we can see along here that the slopes, maybe use another color here, but the slope of a tangent line of any point, so, let's pick this point since it's here. We can see the slope's going to be positive, and that's going to be true for anything in here. So we've talked about this. If it's positive, I know my function's increasing. Something in here, the slope of the tangent line would be negative. It's decreasing from here to here, and then it's increasing again. So the idea here is if the function if the derivative goes from positive to negative, that means the function's going from increasing to decreasing, and it would have a maximum there. So if f prime, if the function goes from positive to, we end up with f prime being negative for some value, then we know we would have a maximum there, right? Because we'd have something that looks like this. Likewise, if it was negative and then it went to positive, then we would have a minimum because we'd have this decreasing and then it would be increasing. All right. So the question though is, how do we identify these points that we should check on either side of, right? We want to find these points and check on either side of them to see if the derivative is positive or negative. Well, we've already talked about those. Those are our critical points. All right. So just a quick review. If you haven't seen or remember from the previous video, a critical point is a point where f prime of C is equal to 0, or f prime of C is undefined or does not exist. All right, so C would have to be in the domain of f. It has to be defined as a function value, but then the derivative, so again here if we look at these points, here we have f prime, we have a horizontal tangent line, so the slope of the tangent line is 0, or the derivative is 0 there. Likewise, the derivative is 0 here. So these are critical points. If you recall, though, in this case, we would have something maybe like absolute value function, like this, and we have this corner point that's not differentiable, the derivative, so this is absolute value of x. The derivative is undefined at that point, but that would be a minimum. Or we could have something like a cusp, where it kind of comes up to a point and comes back down. So again, the derivative would be undefined here, but it's a place we want to check because we can see that over on this side, it's increasing, so the derivative is positive. Over here, the function is decreasing, the derivative is negative. All right, so we have this case here, except it doesn't look like this. It looks like a point. We go from increasing to decreasing. So we want to check critical points. That's ultimately what the first derivative tells us to do is, let's look at the critical point. First, identify the critical points, and then check on either side of them to see if the function is increasing or decreasing. We also have a third possibility here, which is that it's kind of two possibilities in one. We could be on either side of it. We could go from increasing to increasing. So let me just move to another page. We're running out of space here. So another possibility would be that we have the derivative is positive, and then it stays positive on the other side of the critical point. So an easy example that we've already seen, if you looked at the previous video, is something like x cubed. All right. So here we see that the function is increasing over here. It flattens out, right? I may have not drawn it well enough to see that, but it flattens out right at 0. We have a horizontal tangent line. And then you get to the other side, and it's still increasing. So we have a critical point here, because at this point, f prime of 0 is 0. All right, this is the function x cubed. One way to see that is that the derivative is 3x squared, and that's going to be 0 when x is 0. So we know that right at that point, the derivative is 0. But to the left of it, it's positive. To the right of it, it's positive. So it's increasing, and then it's increasing again on the other side. So just to summarize then, if f has a max or a min, all right, and I'm going to just add, this is relative, a relative max or a min. We'll talk about absolute max or a min in another lecture, but if it has a relative max or a min, then, and I should say at x equals c, some point in the domain of the function, then f prime of c is 0, or f prime of c does not exist. In other words, if I have a max or a min, it has to occur at a critical point. This shows you that the opposite is not true. Just because I have a critical point doesn't mean I'll have a max or a min. But if I do have a max or a min, it has to occur at a critical point. It has to occur at something that looks like this, or this, or this, or this. Something like that is where a max or a min will occur. So that's kind of the idea behind the first derivative test, why it works. We know that if a function goes from increasing to decreasing, we're going to have a max. From decreasing to increasing, we're going to have a min. So now let's look at how we would apply this to actually find the relative extremes, or the relative extrema of a particular function. All right, so let's take a look at this function. 3x to the fourth minus 4x cubed minus 12x squared plus 5. All right, and we want to look at where this function has a relative max or relative min. So the first thing is to find the critical points, because those are the points where we might have a max or a min. We're not guaranteed. We might have neither, but those are the places to look for them. So if we first thing is to take the derivative and find those critical points. So it's going to be 12x cubed minus 12x squared minus 24x, and the 5 goes to a 0. Now, if you look at this, this is a cubic. It's a polynomial, so we know it's defined everywhere, so we're not going to have any place where the derivative is undefined. So we won't have any of those types of critical points for this function. So let's set it equal to 0 and see what values of x would make this function equal to 0. So you notice I have a common factor of 12x in each of these, so let's factor out a 12x, and that's going to leave me with x squared minus x, and then minus 2. All right, so let's try to factor that. I would end up with 12x, and then x plus 1 and x minus 2 should do it for factoring that. So now I'm looking at the product of three things, 12x, x plus 1, and x minus 2. And I want to know for what values of x that product is equal to 0. So clearly if x equals 0 here, the whole thing equals 0. In this case, if x equals -1, the whole thing equals 0, and also if x equals 2, the whole thing is 0. So these are my critical points. The only kind of critical points I have are the ones that make it the derivative equal to 0. All right, so now what I want to do is test these critical points to determine whether or not I have a max or a min, or neither, at each of those. So one way to do this that I think is, it helps me kind of think about what's going on. Let's put these basically like on a number line, right? So we know that at x equals -1, that's the smallest, and then we're at 0, and then 2 is going to be out here a little bit farther away. All right, so these are the x values, and I want to look at the sign of f prime. I know that at these points the sign is 0, right? Because we just said the derivative is 0 at these points. But I want to see if this goes from positive to negative or negative to positive in each of these intervals. That will tell me if the function is increasing on each or decreasing on each of these intervals, and help me to determine whether or not each of these is a max or a min. So let's take a look at the intervals that are created here. So I go from, the first one would be from -infinity up to -1. I want to see what's going on out here. I just pick a test point in that interval because we know that the derivative can only change sign if it goes to 0. So it's going to either be all positive out here or all negative, then 0, and then it could possibly switch. It might not, but that's the only place it could possibly switch, is for it to become 0. So a test point, again, I try to make it easy on myself. Let's pick something not too large, and we're going to plug it back into f prime right here. All right, so if I choose, let's say, -2, and let's put that in for x in each of these and see if I have something that's positive or negative. So I'm going to end up with something that looks like -24, and then -2 plus 1, that's -1, and then -2 minus 2, that's -4. So I don't care what this product is, but I have a negative times a negative times a negative, so that's going to be negative, and I know that my function f is decreasing on this interval, so that's negative right there. All right, next interval would be -1 to 0. All right, so picking a test point, I'll choose -1/2. I want to put -1/2 in here, so -1/2 there, that gives me -6. -1/2 plus 1 gives me +1/2, and then -1/2 minus 2, that's -5/2. Again, I don't care so much about the number, I just want to look at the signs. A negative times a positive is a negative, times a negative is positive, and I know that f is increasing. Whoops, there we go. Is increasing on the interval. So along in this interval, it's positive and increasing. Okay then, now looking at the next interval, I've got 0 to 2. All right, so I can choose x equals 1. That's in the interval. And I put it in here for x. I get 12 times 2 times -1. 12 times 2 times -1. That's negative. And f is decreasing. So it's going to be negative in here. And finally, my last interval is from 2 to infinity. I don't know, let's just pick 3. That's reasonable. So I'm going to have 36 times 4 times 1, which is positive. So f is increasing. So notice I'm also finding the intervals of increase and decrease here. So if we think about this as decreasing and then it's increasing, so its shape, it's decreasing and then it's 0 and then it's increasing. So we know that's going to be a minimum. And then from here to here, it's increasing, it's 0, and it's decreasing. So now here I'm going to have a max, and once again I'm going negative to positive through 0, so decreasing, 0, and positive. So here I have a minimum. Okay, so then to summarize, we can say that at x equals -1, I have a relative minimum, and then at x equals 0, I have a relative maximum, and then at x equals 2, I have a relative minimum again. And here are my intervals of increase and decrease. So that's an example. Just to quickly review, we first find the critical points by taking the derivative. determine the points where the derivative is either undefined or it equals 0. And then I'm going to test these intervals in between the critical points. The critical points break up the entire real line into intervals that I can check to see if the function is increasing or decreasing using the first derivative. And then I determine, on either side of these, if it's increasing to decreasing or decreasing to increasing. That will tell me if my critical point is a max or a min, or possibly neither. Okay, let's just do one more example so we can see how this works out in terms of using the first derivative test. All right, so let's take a look at the function y equals x plus 1 over x. All right. So again, we said the first thing we have to do is find the critical point. So let's take the derivative. Derivative of x is 1, and the derivative of 1 over x is negative 1 over x squared. All right. So remember, the first thing we have to do is, I think the first thing to do, as opposed to setting it equal to 0, is to look at what you have and see if there's any place where the derivative is undefined. And we can see that at x equals 0, y prime does not exist. But remember, for it to be a critical point, it has to be in the domain of the original function. And you can see we can't, at x equals 0, the function is undefined. So this is not a critical point. It's just a point of discontinuity, right? Because the function is undefined at 0. So remember, for us to have a critical point, not only does the function have to the derivative not exist at that point, but that point also has to be in the domain of the original function. In this case, it's not. But it is a point of discontinuity. We'll come back to that when we're looking for the relative max and the min. That will be something we have to pay some attention to. But that's one way to find a critical point. The other way to have a critical point is I could have a point where the derivative equals 0. Now notice this is only going to happen when these are equal to each other, right? That 1 equals 1 over x squared. And the only way that 1 over x squared is going to equal to 1 is if the denominator is 1, right? Because 1 divided by 1 is 1. So that means that x squared would have to equal 1. And that will happen when x equals negative 1 or positive 1. All right, so a plus and minus 1. So if we look at, again, this is just the way I like to, helps me to think about it. I'm going to look at negative 1 and at positive 1. Now, when I look at, so these are the x values, and I'm looking at f prime, I know that it's 0 here and that it's 0 here. But I do have to pay attention to this discontinuity, because at the point of a discontinuity, the function can change from increasing to decreasing or decreasing to increasing, because you have a discontinuity. So one example, if you just look at 1 over x, for example, the 1 over x looks like this. All right. So it's possible, you can see here that as we move along here, the function is decreasing, right? The function is getting small, and same thing, the function values are getting smaller here. But if you were to think about, so this is for 1 over x, but if you think about something like 1 over x squared, then I've got something that looks like this. All right? And the function is increasing on this side and decreasing on this side. So it can change. The function can change from increasing to decreasing on either side of a discontinuity. So we need to keep track. Even though the derivative is not 0 or undefined at that point, we need to keep track. We need to break up this interval from negative 1 to 1 using that discontinuity. Okay, so what are the intervals that we need to check then with the first derivative test? Well, I have everything out here, so that's negative infinity to negative 1. So a test value there might be negative 2. All right, so again, here's f prime, and that's what I want to plug my test value into to determine the sign of f prime. If f prime is positive, increasing, negative, decreasing, probably getting sick of hearing that. So let's just go ahead and check it. If I put in negative 2 here, I get 1 minus 1/4. That's 3/4. That's positive. So f is increasing. It's increasing out here. It's positive. All right, now I need to pick something in here between -1. My next interval is -1 to 0, so x equals -1/2. Seems like a good choice. If I put -1/2 here, I have 1 over 1/4, which equals 4. So I'm going to have 1 minus 4, which is clearly negative, and f is decreasing here. All right. Now I have a discontinuity here. I want to look on the other side of the discontinuity in that interval from 0 to 1. So I'll choose x equals 1/2. So again, plugging it in here, well, I'm going to get the same thing whether I put in -1/2 or +1/2 because I'm going to square it. So once again, I get 1 minus 4. That's negative, and f is decreasing here. And then finally, I look at this interval out here, 1 to infinity. And I'll choose x equals 2 as my test point. And again, there's some symmetry here because this is squared. I'm going to get the same value here as I got here, because when I square it, it doesn't matter if it's negative or positive. It's still going to give me 1/4. So that's 1 minus 1/4. That's positive, and the function is increasing out here. So you can see we're going to have something like it's going to go positive. It's going to be increasing 0 and negative out here. And here is going to be decreasing 0 and positive, increasing again. So here, clearly, I'm going to have a maximum. Here, I'm going to have a minimum. So at x equals -1, I have a relative maximum. And at x equals +1, I have a relative minimum. And at 0, nothing is going on, right? It was decreasing. It was decreasing. In fact, if you were to look at the graph of this function, you would see, so our relative maximum will occur at -1. Our relative minimum occurs at +1. And what we have is something that looks like, our function looks something like this. It goes like this here, and then up here, it comes down and kind of goes off that way. So we have a vertical asymptote at x equals 0. And here's my a relative maximum. Notice it's not an overall maximum. All of these points are bigger than this. But this is a relative maximum because on either side of this, the function values are smaller. And likewise here, this is relative minimum because function values on either side of this point are larger. All right, so that's what the first derivative test is, and that's how we apply it to determine the relative extrema of a function.